Hi everyone, welcome back. Today we're doing unique Morse code words. International Morse code defines a standard encoding where each letter is mapped to a series of dots and dashes as follows. So the character A maps to dot dash, B maps to dash dot dot dot, and C match to dash dot, and so on. So for the full table of 26 letters, they are mapped given below, where the first string maps to A, this maps to B, and this maps to C. So given the array of strings words where each word can be written as a concatenation of the Morse code of each letter, CAB can be written as dash dot dash dot. So this represents C, and we have A, which is dot dash over here, and we have B, which is dash dot dot dot, like this. So this is just a concatenation of CAB in Morse code, and we will call such a concatenation the transformation of a word. So we have to return the different transformations among all words we have. So in this case, we have Jin, Zen, Gig, and MSG. So in this case, we get these corresponding transformations over here. And there are two different transformations, this and this. So we have to do some deduplication of the transformations as well. So in this case, it seems that Jin and Zen give the same transformation, and Gig and MSG returns back the same transformation as well. So if we deduplicate them, we get 2, and that's why in the output we return 2. So it seems that the task would be to convert each of them into transformations and deduplicate them as well, and get the length of distinct transformations. For the second example, we have A. So in this case, it's just one transformation. The constraints would be where words range from 1 to 100, and every single word inside this list ranges from 1 to 12 characters. So these are pretty lenient runtime constraints. So let's do this. So the first approach would be to map each of the word in words to their respective transformations. And we can get the corresponding transformation by converting the letters into an index that corresponds to the index in this list of transformations over here. So for example, if we do A minus A, then we can get an index of 0. So I guess we can convert this to the hexadecimal ordinance number over here, and we can subtract this by the ordinance of this A into a character. So that might work. Let's try that. So just to test this out, let's try converting A into an index. So let's do index equals to odd of A minus odd of character A, and let's see if this returns an index 0. Okay, so yes, it does give us back 0. And for our viewers that are new to this concept, ORD in this case will return back the ASCII representation that maps this character to an integer. So every single character can be mapped to a corresponding number, and this number is that same number that is found inside the ASCII table. So if you pass in odd A, in this case, this will give us back a corresponding number that corresponds to A's position in the ASCII table. So I will link a link to the ASCII table so you can take a look at that. But what I'm doing here is I am mapping each of these characters into their to a corresponding index inside this list. So if you take, and because every single character in this input is guaranteed to be lowercase English letters, what we can do is we can take each character and subtract this by A, and this will give you back an index inside this list over here. So if you take the ordinance of a character, subtract by A, that will give you the corresponding index inside this Morse code list. And that will give you the corresponding transformation for that character. So that was quite a mouthful, but just to show you how this will work, if you take odd of A, this will give you back 97 as we saw. If you give it let's say if you have a character which is B, if you take the odd of B, of char, this will give you back 98. And if you take odd of char minus odd of A, that will give you 98 minus 97, giving you back 1. And this 1 is really the index of B. So what you can see is index of 1 inside this list would be dash dot dot dot, and this corresponds with the transformation of B. So using this property of the ordinance of characters, we can map each character into the corresponding index inside this full table here. So yep, this would work. Now that we have a way to map each character to their Morse codes, we can then proceed to concatenate all transformations for each character in the word and get a full transformation string. We can then add this transformation string into a set. The set would deduplicate duplicate entries, and we can just return back the length of the set to give back the unique Morse code representations. So yeah, that looks great. So the algorithm will look something like this for word in words, and for char in word, we will do char transformation equals to, let's get the char in char Morse code index to be equals to ord of char minus ord of A. And we will use this char Morse code index to get the corresponding full table. So let's call this full table. This is a list of string, and we will set this to the full Morse code table. And the char transformation would just be the char Morse code index inside this full table, giving us back the char transformation. And over here on line 14, just before the for loop, let's define full string transformation, and we can set this to an empty string. Let's append this with the char transformation on line 17. And now that we have this full string transformation after line 15 to line 18, let's have a unique Morse code words. Let's set this to a set of string and define this as a set. And we can add this full string transformation that we have inside this set. And once we get the transformation for all words and add them into the set, by the end of this for loop over here on line 14 to line 20, the answer for the number of unique Morse codes will just be the length of this set. So that's pretty much the algorithm. So we will first implement this, and we will try tracing this out with a sample test case. Actually, this is pretty much the algorithm, but I will just type it out again just to articulate the thought process clearer one more time. So let's first define the full table. The full table is given to us inside the question. Let's set this to a list of strings, and let's copy this table here. And this is the full table for mapping a character to the corresponding Morse code transformation. The next step will be to define a simple set, unique Morse code words, This will be a set of string, and we'll initialize this to an empty set first. We're now ready to iterate through all words. Let's define a full string transformation. And this empty string will be used to accumulate the transformations for every single character inside this current word. So let's start iterating through every character in a word. And let's get the corresponding Morse code index for this current char by taking the odd of char minus odd of a. And now we can get the char transformation by using this index to fetch the corresponding transformation for this character from the full table. So just like this, we got the char Morse code index. We get the char transformation. Then we will just append this char transformation into the full string transformation. And once we're done, after we go through all characters in the words and convert them into their Morse code representation and append it into 30, line 30, full string transformation will contain the full transform Morse code. So we will add this into this set over here. So the set will take care of the deduplication for us. So after we have went through all words and get their corresponding transformations and add it into unique Morse code words, we can just return the length of unique Morse code words. And that's pretty much the answer. So to see that we got this right, let's quickly go through the first example. So words is equals to Jin Zen. Let's clear this. And now let's see. Yes, that's the only test case there. So now let's start iterating through the first word. This will be Jin. And in this case, for char in word, let's set char to be equal to G. In this case, G would be the odd of char, as we saw is 97. So something minus 97, char 97. So A is 97, B is 98, C is 99, D is 100, E is 101, F is 102, G is 103. So 103 minus char 97, that will give us back 6. So the corresponding index for G would be 0, 1, 2, 3, 4, 5, 6. So this is the char transformation. So let's quickly check if this is the right answer. We can see that, yep, G is indeed dash dash dot. So the full string transformation will be concatenated will have this char transformation. Let's trace full string transformation as well. So let's set this to be equals to this task far. And we will continue with the next character. So I, A, B, C, D, E, F, G, H, I, 9. So 9 minus 1, 8, because it's 0 index. So this is 8. So 97 plus 8, that gives us 105. 105 minus 97 is 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is dot dot. This char transformation is dot dot. Okay, I hope I got this right. But let's see if I'm right. Okay. Yes, it's indeed dot dot. So looks good. We will append this to full string transformation again, dot dot. So now this is our current full string transformation. Now let's go for N. A, B, C, D, E, F, G, H, I, J, K, L, M, N, 14. 14 minus 1, 13. 13 plus 97, 110. Minus 97, this gives us back 13. 113, 13 plus 97, so should be right. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So dash dot. Is it dash dot? Yes, it is dash dot. So the corresponding Morse code for n is dash dot, giving us back dash dash dot 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 dash dot dash dash dot 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 dash dot. Yep, we got the full string transformation for Jin. Okay, I'm really lazy to go through the rest of the transformations, but you get the idea. This works. So this will give us back this result, and this should deduplicate it well. So this should be enough tracing. Let's run this against some test cases. So let's run this against the sample test cases. This passes, and let's submit this. Yeah, it works. So the time complexity in this case, if the length of words is n, n is the number of words, then in this case, we would have, it will be on over here because we iterate through every single word. The calculation over here is O1. It's just a subtraction over here. And item access in the list by index is O1 as well. String concatenation is O1 as well. And adding a character to a given set is O1 as well. Okay, one additional detail is that we are iterating through every character in a word. So let's define m to be the number of characters in words. Then in this case, this iteration for characters in words would be OM. So the total time complexity would be ONM. So sounds about right. So okay, that's our time complexity. Now let's go through our space complexity. So let's remove our workings for the time complexities, and let's see. So we have a full table over here. So this would take up to 26 inputs regardless of n and m. So let's say this is O1 because this is constant regardless of n or m. And unique Morse codes works will contain the same number of full string transformations, deduplicated full string transformations, but let's just assume the worst case scenario is if all transformations are unique inside the words. So in this case, the worst case would be ON. So that's pretty much it. Of course, the length of the transformation would scale with respect to the number of words in each word. Sorry, number of characters in each word, but let's just keep it simple and just say the space complexity is ON. So yeah, that's pretty much the time and space complexity of this algorithm. So I hope this was useful. I hope that the tracing process let you better understand the question and also let you see how we can test if the algorithm that we have is correct. So that's pretty much it for this video. If you like it, please give us a like and subscribe, and we will see you in the next video.